All right, I had no questions emailed to me early today. So whatever questions are out there are going to be asked by whoever's working in the background. So if you don't have any questions for me today, I'll just pick back up the banjo and get working on that again. Sawhorse class, we should be able to go through converting Sawhorse and line figure drawings into Fischer projection. Sure. So, big thing to recognize difference between something like a Sawhorse and a line drawing versus a Fischer projection is that a Sawhorse or a line drawing is actually what we're seeing in three-dimensional space with the molecule. So if we have a line bond drawing that looks something like this, and we'll just put halogens on here to make them easy to identify, or something that looks like this. Chlorine, hydrogen, CH3, chlorine, hydrogen, CH3. These are actual representations of, yeah, you're welcome. These are actual representations of the spatial geometry of the molecule. This isn't true of Fischer projection. A Fischer projection is going to be where each backbone atom here is represented by the next atom and the backbone going back, and whatever atoms are perpendicular to that backbone coming out at you. So Fischer projection is going to be different than the actual drawings we have here in terms of true spatial arrangement. The big thing with the Fischer projection is tweezing out what are the chiral centers. So the way I teach it, the way you start by drawing a Fischer projection, particularly if you don't have chiral ends, so we'll start with this line bond drawing first. If you don't have chiral ends, just go ahead and make those the ends of the chain. Now, if it happens to be chiral, then you're going to need to include the carbon, and your end is going to be one of the atoms, so something like a hydrogen, chlorine, fluorine, something. But generally speaking, when we do a lot of these drawings, it's rare that either end is going to be chiral. Each horizontal line here is going to correspond to one atom in the backbone. Now, easiest way to take a line bond drawing and convert it to something like a Fischer projection is to build the molecule. So first what I'm going to do is I'm going to show it by building the molecule, and then I'm going to talk about how you would do it if you're trying to do it from the projection. So in this case, I've got 1, 2, 3, 4 carbons. And I'm going to make my fluorine blue, and my bromine, or I'll take my chlorine. I make chlorine blue and my bromine red. Those should be fairly easy to contrast in the camera. So everything that is solid, we're going to put in plane. So I've got my zigzag here, and then I've got my bromine coming out, my chlorine going backwards. Now, in order to convert this to a Fischer projection, what we need to do is take the backbone and turn it into a coil or a loop. So we're going to do a rotation here to translate this into a structure. When we do the rotation, chlorine's still going to be on the backside, and we do it bromine's going to be on the back side. So when I rotate it, I end up seeing that I've got hydrogen, hydrogen, and bromine, chlorine. So my bromine, if I look at it down the chain, sorry, back up. So to do the Fischer projection, take the top atom, and you're going to start rotating that coil and looking and seeing what you see. So if we look here, we've got the bromine on the right side, and we've also got the chlorine on the right side. Now, reasonable thing to ask is, well, what if I start from the other side? What if I start with the side that actually has the chlorine on it? What you're going to see is that if you start from the other end, it's just going to be this figure rotated 180 degrees. So now I start out with my chlorine on the left and the bromine on the left. So honestly, it doesn't matter which way you go. You should get the same answer. Now, how you would convert this in terms of trying to draw it without a model, I don't advocate this. Modeling kits are built for this very reason. But if you want to try, you need to rotate the molecule so this way it ends up forming a coil. So if we had more carbons in this chain, we would have to rotate successive bonds to end up getting this coil. Now when we do this rotation, everything that's a wedge is going to be flipped to a dash and vice versa. So our bromine is going to go back, whereas our chlorine is going to stay where it is. And if we wanted to do this carbon, we would need to rotate this molecule and bend that carbon around. So you can see how this is really difficult to do just on a drawing. Now there's also a sneaky pattern that's built into this as well. These alternate. So if we're going to say chlorine is our anchor atom, we're just going to alternate the wedges and dashes. So since, okay, we'll get to that one next. But anyway, you would rotate it and then you would arbitrarily turn it. If you want to turn it left, so rotate it out with the chlorine swinging out, the bromine and chlorine on the same side. If you rotate it the other way, you get the chlorine on top and the bromine on bottom. Now, the trick you can use, and I don't advocate it, again, just build the modeling kit. If we draw any type of long drawing and work it out, because of how rotations work, a wedge is going to be the same side as the Fischer projection as the dash on adjacent carbons, and it's the same side as a wedge on two carbons apart. And the same is going to be true for wedges, or a dash. A dash is going to be the same side as anything that's on a wedge on adjacent carbons, and anything that's a dash two carbons away. And for bigger chains, it would work out that if we look at the position, so let's say this is our starting position. Well, this is one carbon away, 2, 3, 4, and so forth. Every even numbered carbon, if they're a wedge, they're both dashes, they're on the same side of the Fischer projection. If they're both wedges, they're on the same side of the Fischer projection. If they're opposite, then they're on opposite sides. Whereas all the odd numbered carbons, they have to be opposite to be on the same side of the Fischer projection. So how about the Sawhorse drawing? Again, all Fischer projections are going to be drawn with this line up and down. Again, if we have achiral ends, we're just better to represent them. And then each carbon along the backbone, again, is going to represent a dash. Now, again, I'm going to advocate you build this model first. So if we build this model, so we'll make the chlorine red again. And we'll make the fluorine blue. All effectively line ball drawing. Yes, so in this case, because one starts out wedge and one starts out dash, and they're on opposite sides because they have opposite wedges and dashes, they end up being on the same side. Now, if they were two carbons away and they were wedge and dash, they would be on opposite sides. It would have to both be wedged to be on the same side. All right. So if I build this model, I've got the CH3 going up, the CH3 going down, and I've got the fluorine going up and to the left, and the chlorine going down and to the right. Again, now that I've got this built, I'm just going to turn it and make it into a coil. This time they're both going to be on the same side again. So I get the chlorine and the fluorine on the same sides. Now, this is kind of approached the same way you would draw a do it from a line bond drawing. All Sawhorse drawing really is just this line bond drawing turned at an angle. So if we identify the backbone here, it's just 4 carbons. And if in this case I want to rotate it so this way this chlorine group is being pushed into the board, this fluorine group is being brought into the board, that's going to push my chlorine out and my fluorine in. So there's a few methods here. You can build the model. You can try to recreate the line bond drawing just by trying to identify the backbone and rotating the molecules so that the backbone all sits in plane. The other way to do it is, again, we know for this Fischer projection, all the backbone has to be forming a coil. So we would rotate along this bond, and to get the CH3 group down, we would need to rotate everything 180 degrees. So our chlorine would be up and to the left, hydrogen would be to the right, fluorine would be up and to the left, and hydrogen would be on the right, and makes that Fischer projection a little bit easier to see. But yeah, that's how you convert those two, the line bond drawing and the Sawhorse projection, into a Fischer projection. And again, it doesn't really matter with which end you start on. If you start from a different end than someone else, you're going to get the same structure, just rotated 180 degrees. Hey, you're very welcome. This is the hardest part of the material in Orgo 2, is the characterization and getting comfortable with the different projections. These are all tools that you're going to use down the road, and Professor Asaka and I take the same approach with this, is that if you can get this down, the analysis of alkanes gets very easy. The hardest part of alkanes is really cyclohexane because there's a whole bunch of different conformations. But if you can understand how to read a Fischer projection and you can understand how to read a line bond drawing, it begins to make a lot more sense why you're seeing what you're seeing. Like, it makes, in my opinion, it makes it a lot easier to see what are considered axial and equatorial bonds, but you're not there yet. But yeah, if you can survive this chunk of material, you should do fine for the rest of organic. We want to front load the course. Other questions out there? Some of the questions on page 27, 29 regarding constitutional isomers in the test packet. I'm going to guess that's the horrible nightmare one where it asks you to like predict all the possible combinations. So let me bring it up. You said pages 27 through 29. So 2020, let me share the desktop with you. So for this question, for the following formulas, draw or name all possible constituent isomers if one hydrogen is replaced with a bromine atom. So this is more going to be a draw than name at this point. So I've got, and this is given to you as a Fischer projection just to make it a little bit easier. So if one hydrogen was replaced with a bromine atom, we're just going to start looking at hydrogens. So let me switch this back to my view. So let's identify where the hydrogens are. We've got a hydrogen here, 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 and here. So part of it is just considering symmetry. So if we replace one of the hydrogens here with a bromine, we get CH2, Br, CH3, H, 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 H. That is one possibility. Now, we could also replace it on the other end of the chain, but the thing is that if we replace it on the other end of the chain, we just rotate it 180 degrees, we get the same thing back. So this is one unique possibility. Putting bromine down here is not another unique possibility. The other thing is that there are two hydrogens bound to this carbon, which means it's achiral. So there's only one way we can attach this bromine to this molecule uniquely. Now, we go to the next one. And let's say I put it on the right side. Well, if I put it on the right side, now I've generated a chiral center. So there's actually two ways I can attach this bromine and get a unique molecule. So I can attach it on the right, or I can attach it on the left. So far I've got 1, 2, 3 possible constitutional isomers. These are ways to connect the atoms differently and get a unique answer. Now, next hydrogen down. So if I attach a bromine here and I look at it, it's not a chiral center anymore because below it I've got this CH2CH3 group and above it I've got a CH2CH3 group. So there's only one unique way to attach a bromine to this atom. Now, if I attach to the next one down, I'm right back to where I was with these first two. So these are the 4 different possibilities for the different constitutional isomers you could get for that first problem. The rest of these are going to kind of follow that exact same line of reasoning. Go through and start substituting out a hydrogen and see what you get. Let me share the desktop with you. So if we look at the next problem, there's a CH3, CH3, H, H, H. If I replace a bromine at the top versus the bottom, well, these are different molecules because one has a bromine on a carbon that's adjacent to this HCH3 group, whereas this one's adjacent to two hydrogens. So there's one combination, one bromine replacing a hydrogen on each N group. We can also replace a hydrogen on the carbon, this methyl group on the left, and again, because all 3 of these CH3 groups have 2 hydrogens, there's no chirality, so we end up with a unique solution. If I replace the bromine here on the right, this isn't a chiral center because there's 2 methyl groups attached to it. So there's only one unique possibility here, and then I just start working my way down. If I put a bromine here, there's a chiral center, so I got to do both chiralities. If I replace bromine here, I've got both chiralities. So it gives me 2, 4, 5, 6, 7, 8 possible unique isomers. So yeah, it's actually not, if they look intimidating, they're not really that intimidating. The big thing here is just replace a hydrogen. If it's a chiral center, then you've got the enantiomer that can go with it. If it's not a chiral center, check for any type of rotational symmetry that will give you, like, can you recreate one you've done before, and then you can start tweezing them out. But the point of that problem is more to get you to start seeing symmetry and recognizing the different types of isomers that there are out there. There are lots of ways that you can connect these things. Yeah, you're welcome. Other questions? All right, well, I'm here if you got questions, so just put them up in the chat. I gotta warm up again. Can we go over how you get the Newman projection on page 18 of the study guide? I know exactly which one you're referring to, too. Yeah, this is actually a kind of a fun problem. It's a nice challenge problem for students. So I'm guessing the reference here is to this top problem where we've got this thing, and you're actually looking across a bond that is not a solid line. And it wants to know whether this carbon and this hydrogen are gauche, anti, or eclipsed. So if you give me just a minute, I'll draw it up on the board. Oops, drew that wrong. All right, let me switch it back to my view. So the way you would approach this problem, I would highly encourage you to build the molecule. If not, what you're going to do is you're going to have to rotate, come on, get back to focus, you're going to have to rotate this molecule into the board along this bond, along this carbon bond. So if you want to try the rotation, what's going to happen is that you're going to have to rotate, let's see, that carbon's back, you're going to have to rotate that fluorine. No, build the molecule. We're not going to try to do it by rotation. This is definitely one you need to build. Now, these CH3 groups were intentional to basically make it so you're not dealing with a lot of heteroatoms up here. But if you build this molecule, so we'll let blue be the fluorine, we've got our backbone, so CH3, carbon, carbon, carbon coming, methyl group coming forward, fluorine going back, and we've got our carbon sitting up out of plane. And we want to know the relationship between the hydrogen and the carbon. The first thing we're going to do is we're going to draw a Fischer projection looking along this bond. So to get to that bond, what I'm going to do is I'm going to just grab the bond itself. Of course, you rotate it out of plane. We're going to grab the bond itself and we're going to turn it so that we're looking down it with the front carbon eclipsed from the rear carbon. So when I do that, that front carbon, hydrogen coming up, CH3 going down, fluorine going back. The CH3 group, oh, blame it. No, hold on. Sorry, looking at the wrong carbon. When I do that, this is an obnoxious problem. I'm glad it's in there. So if I grab it, I've got a CH3 group going down, an H group going down, and then I've got this CH3 F carbon coming up. And that's just the way I've chosen to rotate it. If I look behind it, I've actually got 3 hydrogens. Sorry, a little hard to do this from my angle. 3 hydrogens sticking out from behind. So in terms of this carbon versus this hydrogen, they are both solid lines, so that's going to make them anti. And they're zigzag, so that's automatically going to make these anti. And that's how you would draw the projection. But I would definitely say this is one of those problems you need to build it with a modeling kit. I cannot conceive of how you would rotate that in order to get any of those answers. Now, that said, you could quickly tweeze out that the carbon and the hydrogen are anti because you see the zigzag pattern, and they're both solid lines. Yeah, that sucker's a hard problem. I would tell you not to expect anything that hard on an exam. Other questions? Of course. The last page of the study guide. Ah, that fun problem. So can we go over enantiomers versus diastereomers in the test packet? Let's do the enantiomers versus diastereomers first, and then do the last page of the study guide. So enantiomers versus diastereomers. We'll work the first problem. So in all of these that you're given the relative configuration. So it's not saying which combinations you have, which like RS you have. It wants you to figure out all of them, and it wants you to figure out which ones are enantiomers and which ones are diastereomers. So there is actually a very efficient way to do this, and again, this is with the Fischer projection, because the Fischer projection is designed to help you quickly tweeze out what the chiral centers are and what their different chiralities are, what the different combinations of chirality are. So I'll take this first example. I've got it drawn up on the board behind me. So the first question is, what are the chiral centers? And if we look across the backbone, we've got these two as chiral centers. So their spatial relative, or their relative spatial orientation, their R and their S, is going to really matter how they're oriented, whether they're drawn as wedges or dashes. So if we draw a Fischer projection, CH3, CH3, so those are two CH3s, and we've got 3 backbones. Center one's 2 hydrogens, so it doesn't matter. The question is now, which way do we orientate the hydrogen, the OH and the Cl? And the answer is it's arbitrary because we're going to generate all of them. So which one we start with first doesn't matter. So I like to put things on the right. So we'll have an OH and a Cl. So that's my first stereoisomer. Now, I'm going to highlight the chiral centers here. An enantiomer is defined as a molecule where 2 molecules where all the chiral centers are opposite. So if they're R symmetry, they go back to S. If they're S, they go back to R. The way this looks in a Fischer projection is we rotate things horizontally or vertically across a bond. Traditionally, we do it horizontally because it's a lot easier. So if we wanted to know the enantiomer of this one, we would just swap the OHs and the CLs. Now again, if I were to draw a mirror, this is what I get. So if I take a literal mirror image of this, these two are enantiomers. A diastereomer is defined as a compound where we have changed at least one chiral center, but not all the chiral centers. So we have to have more than one chiral center in order to produce a diastereomer. So in this case, the top two, we switched both the OH and the Cl, and that's what made them enantiomers. Now let's just switch one. So since we can choose anything we want, I'm just going to switch the hydroxide, or the OH, the alcohol group. So because I flipped just the OH but not the Cl, this is a diastereomer of both of these. Because even though this has the OH flipped, it's also got the Cl flipped, which this one doesn't have. The mirror image of this would have the chlorine and the hydrogen flipped and the hydrogen and the OH group flipped. These two in blue are enantiomers. They have flipped symmetry, so both the OH and the Cl flipped, but they are diastereomers of the two compounds above them, because this one, even though it's got the Cl and the H on the same side, this isn't true of the H and the OH. They're on opposite sides. And if we compare it to this one, the H and the OH are on the same side, so we flipped one chiral center, but the H and the Cl are on, the H and the Cl are on opposite sides, so we flipped one chiral center, but the H and the OH are on opposite sides, so we haven't flipped all of them. So to figure out the number of potential stereoisomers, is 2 to the number of chiral centers, or 2 to the n. Now this is potentially. And the reason I say potentially is that if we end up with a mesoform where there's a mirror plane, then that's going to get rid of one of our possibilities. But that's how you do the enantiomers versus diastereomers. Figure out your chiral centers. Draw the Fischer projection is the easiest thing to do because it will highlight all the chiralities and make it easy to figure out how to switch them. And to figure out something's an enantiomer, you just see if it's the mirror image and if everything horizontally is flipped if there is a difference. Now, last page of the study guide. This is a really good problem. I updated the packet to give you tables of information just to make it a little bit clearer to see what's going on. So if you haven't downloaded it from the course pack since this morning, it is up there. There's also a few changes to the key because people did find a few mistakes. But I'm going to bring up the revised version just so you can see the key, so you can see the table. Now, analytical techniques. So I'll start sharing my desktop with you again. And this is a problem that if we were doing a traditional CETIC course, we would work through this as a group. So first thing you see here is the carbon-13 NMR spectrum. And carbon-13 NMR is going to tell you how many unique carbon functional groups there are in the given molecule. So we have 4. The solvent peak here at 80 is ignored. It's just an impurity. Typically, we see solvent impurities in these NMR spectra unless they're generated through simulation software. And that's also how we calibrate the machine. But the thing to note here is that, 1, we have 4 unique carbons in this compound. So I'm going to write that up on the board behind me. So the NMR tells me I have 4 carbons in their 1-to-1 ratio. So whatever molecule I end up generating has to have 4 carbons in it. The second piece of information, the 1H NMR tells me that I have 3 groups of hydrogen. Now, hydrogens can appear on carbons, oxygens, and nitrogens. The reason why I don't think I would not assume that there's nitrogen and oxygen in this is because of these chemical shifts. You're between 0 and 3 ppm, so this is implying that these are CH2, CH, CH3 groups. So I have 3 peaks, a 2.45 that has 2 hydrogens, and these 2 hydrogens are a quartet, meaning that they C3 hydrogens on adjacent carbon. We have a singlet with 3 hydrogens that don't see any hydrogens on adjacent carbons. And then our last one, our 1.05, is a triplet. So we have 3 hydrogens that see 2 hydrogens. So let's take a step back here. Let's talk about what the NMR data shows us. So we have 4 carbons. Now, 3 of these carbons contain hydrogen, which is implied from the 1H NMR because that's a chemical shift for a methyl group. So one of these carbons does not contain a hydrogen. So we have a carbon, and then we have 3 other carbons that do contain hydrogens. Now, one of those hydrogens doesn't see any other hydrogens, so it's a CH3 that isn't attached to something with hydrogens on it. Now, we also have a carbon with 3 hydrogens, and it's adjacent to a carbon that has, so we have our 3 hydrogens, and it's adjacent to a carbon that has 2 hydrogens, and we also have 2 hydrogens that are adjacent to a carbon that has 3. So we have the CH2-CH3 group, we have a CH3 group, and then we have an additional carbon that's floating around somewhere. Okay, so what does that tell us so far? Well, one, we know that we have a CH2-CH3 group, we have a CH3 group, and we have a lone carbon. So if we go back to the packet, now we've got mass spec data. And the mass spec data is going to tell us how much this compound weighs. Now the parent ion here is at 72 AMUs, and that's an important number. Because we already know how many carbons and hydrogens we have in this molecule. We have 4 carbons, and we have 8 hydrogens. So 4 times 12 is 48, plus 8 gives us 56 AMUs just due to the carbons and the hydrogens present in the molecule. So we have an additional 16 AMU that we need to use up in order to account for the rest of the weight. So right now we got 56 AMUs. We need 16 additional AMUs to make up for it. This could be nitrogen, this could be boron, this could be a whole bunch of other elements, but there's only one element on the periodic table that weighs 16, and that's oxygen. So this will imply an oxygen. So if it is an oxygen, there are definitely peaks in the NMR that will show up to describe the oxygenal functional group. Because remember, we don't do oxygen NMR. It's too expensive and it's too rare. So our IR will tell us if we have an oxygen, if so, what type of functional groups it's involved in. And if we go to, the IR, we actually have a ketone stretching mode in here. So this 3000, where we've got a peak here, peak here, peak here, that's definitely due to our CH3, CH2 groups. But then we had this really sharp peak here about, looks like 1700 AMU, 1700 wave numbers. That's a ketone group. So we definitely have a C double bond O in this molecule. So we got a C double bond O, we got a methyl group attached to something that doesn't have any hydrogens on it, and we've got the CH2-CH3 group that's attached to something with no hydrogens on it. The only way we can really make this work out is to put the ketone between the two of them. So this ends up being the only molecule that is consistent with all of this information. And this is kind of the thing to say a lot with NMR and IR and mass spec and any other type of analysis. The only thing you can say is that it is consistent with. Now, I would say this is proof this is the molecule you have, not because of each individual, but because of the sum of all 4 measurements. You definitely have a ketone. The ketone is going to be consistent with the NMR. It's also going to be consistent with the carbon-13 NMR. It's going to be consistent with the mass spec. There's no other way to pair these atoms up and come up with a unique solution. Now, I'm sure someone could probably come up with a clever answer, but I intentionally picked this wrong because it is so simple. The molecule is so simple, there's not a lot of other combinations. But that's how you would actually use these techniques in practice. Now, again, you would never see anything that insanely difficult on an exam because you just see, I've taught this enough times, I can quickly see how to explain it. But this is actually how it's done in practice. You don't blindly go at something. You usually have a pretty good first guess. So whatever you end up deciding is the answer, it has to be consistent with all the pieces of information you're putting together. And with some of those packet problems, you will see that there's more than one answer, and that's by design. I want you to get out of the habit of thinking that a single measurement will tell you everything you need to know. Particularly with organic, it's a lot of measurements that will, on their own, don't prove that you've made what you think you've made, but taken together, that's kind of the only explanation. All right. You would actually look it up in a table. So on the course website, if you're in my organic courses, if you go to the lesson 1, test 1 drawing, there are, stop it, test tables of common 1H, 13C, and IR values. And I don't require students to memorize this. I find it particularly not that useful to memorize these values. You will learn them by osmosis, but to make you memorize them, we have these tables for a reason. So if we go to IR Spectroscopy Peaks, your ketone peak here is 1620 to 1680, and if we look at it, we see a sharp peak in that range. So we definitely expect to see a CO in that range. Now, we can also get a 1620 to 1680 for a CC double bond, but we don't have any evidence of a CC double bond in term. A CC double bond would not be consistent with the mass spec we're seeing. And you see that with a lot of these peaks. Like there's just a lot of peaks that don't sit in a range that makes sense. Yeah, your aldehyde ketone sits roughly in that range too, 1710 to 1750. But this is just tabulated values, and you would look for a peak in the IR and see where the peak kind of makes sense. And we'll talk about more as we get into specific functional groups later in the semester. Unique IR bending modes that really correspond to those. So alcohol, there is sort of a diagnostic peak for alcohols and amines, and sulfides, things that have SH groups, or thiols that have SH groups. And if you have reason to believe that oxygen or sulfur or nitrogen are in your compound, you could verify the presence of the compound by looking at the IR. IR serves two purposes. If you don't have a set of databases to compare to, it will tell you the behavior of what we consider heteroatoms. So nitrogen, oxygen, and carbon. Or mostly just nitrogen and oxygen. So oxygen and nitrogen aren't really used in terms of NMR. We don't probe them that way because of how they're not really that responsive, or the isotopes that aren't that responsive. So we would use the IR to verify like what oxygen is doing in the molecule, or nitrogen or sulfur is doing in the molecule. We use the 1H NMR to figure out what the hydrogen is doing in the molecule. We use the carbon-13 to figure out what the carbon is doing in the molecule. And we use the mass spec to figure out what the molecule looks like. And on top of that, the mass spec has fragmentation patterns that we can use to verify if certain things are there. So for the molecule behind me, we've got the CH2, CH3. So if we were to look in the IR spectrum, if this is really the compound, we should see a peak corresponding to a CH2, CH3. So that's 24 plus 5. We should see a peak at 29 AMU. And if we switch back to that table, or back to that problem, there's your peak at 29 corresponding to that CH2, CH3 fragment. We also see the other half of it. So this thing weighs 72. So we got the peak at 43. And that corresponds to the other half. That's the other half of the ketone with that CH3 group tacked onto it. But to reiterate, like, I'm not going to make you memorize the bending modes. We have tables for that. But as we get into the semester and we start talking about specific functional classes, so alkanes, alkyl halides, alcohols, we'll talk about diagnostic tests for those. Alkyl halides are actually very hard to identify with IR. It's usually their mass spec where we see that they're there, because chlorine actually has two stable isotopes. It has 35 and 36. And so what you see with a lot of chlorine in mass spec is double peaks that are the same height because those two isotopes are the same. Bromine's kind of the same way. We end up seeing a massive atomic weight associated with the bromine. So the mass specs are better for your alkyl halides. Alcohols are better done with IR. All right, other questions? Sorry, I just really enjoy analytical chemistry. Really wish we taught it, but yeah, I'd have to go to a four-year university to do that. On pages 49 through 57, we're supposed to match the options with the peaks. Let me bring it up, 49 through 57. So you're supposed to determine, I guess I should share that with you. So for these pages, you're trying to figure out which of these molecules, if any, and how many are self-consistent with the molecule, with the NMR spectrum that's showed. So if we look at the first example, I'm going to have to back this off. I know it's going to be hard to read on your end, but just to kind of give you the big picture here. We have two functional groups, A and B, that both contain hydrogens, and they look the same. So if we look at all these molecules, we do see that there's a mirror plane symmetry. So we have these two CH2 groups look the same, these two CH3 groups look the same, this CH3 group looks the same as this CH3 group, CH here. So the next thing we have to do is we have to look at the splitting pattern. So we have a doublet, which implies one adjacent hydrogen, and that contains 3 hydrogens, and we got a doublet plus a quartet, which contains 1 hydrogen. So your butane here is not consistent with this type of NMR splitting pattern, but A and C are. So you would say then that A and C are consistent with the spectrum, but that's all you can say. It's not that compound A is consistent with peak A and compound C is consistent with peak B. That doesn't make any sense. The question is if the molecule overall would be reasonable to say that it would generate that type of NMR spectrum. And again, you will find with some of these problems that there is more than one answer. Sometimes there's uniquely one. But it's to kind of get you out of that habit of believing that NMR is this black and white thing that, oh, it's only going to give me one answer. It can give you multiple answers. There's a lot of things that could be consistent with it. The point is, can you show that it's consistent with it? Can you figure out which molecules would be consistent and discount ones that wouldn't be? And for those looking to answer the philosophical question, when in science does it stop being consistent? When does it stop being proof? It starts being proof when the likelihood of an outside answer goes to 0. The likelihood of a second explanation goes to 0. So particularly as we move on through the semester, we'll talk about given reactions. And if you're just working with something like a 5-ring carbon, a cyclopentane, it doesn't make sense for you to believe that there's a 10-membered ring floating out there for no apparent reason. Like, we're not proving a negative argument so much as we're using likelihood. And actually, that's how most of science works, is that we have a set of assumptions, and as long as those assumptions are reasonable and tend to hold up, we're willing to say that we have proven our point. Until we have outside data to show otherwise, it is proven enough. So if you're doing a synthesis and you know what your reagents can do, it doesn't make sense to say that you probably had something that they can't do occur. And so we use the context of the experiment and the IR and the characterization data to, if they're consistent with it, to prove what happened. Priority on a molecule with question 38 on the homework. So let me bring up question 38 on the homework. And with the homework assignments, keep in mind it does sometimes draw from a pool. So if you're seeing a different question for me than you are for you, but it's qualitatively the same information, it's probably because it's giving me a different pool question. Question 38. So what does the absolute configure RS, the molecule, represent by the Fischer projection shown here? So the molecule it's showing me So first things first, we're going to look at the chiral atom, and we're going to look at what's bound to it. So we've got a hydrogen, oxygen, and carbon bound to it. So if we use the CIP priority rules, this is lowest priority, this is high priority, and then we have a carbon here. So how do we assign priority to the carbons beside it? Well, what we're going to do is we're going to write out the element, and we're going to write out what it's bound to, and we're going to write out each bond as if it's a single bond. So in this case, it's bound to the oxygen twice, so we're going to treat those as if it's bound to 2 different oxygens. So we have oxygen, oxygen, hydrogen. This one's bound to an oxygen and 2 hydrogens. Now, we're going to arrange these in terms of decreasing priority. It's hard for me not to do this at this point, but if you can't do that off the top of your head, it's perfectly fine just to write out the 3 bonds and then organize them up here. So next we look for the first point of difference. So the first bond is to an oxygen, that's the same. This one's to an oxygen, this one's a hydrogen. And so this has the higher priority, so this would become number 2, and this would become number 3. Now, how would you figure out whether it's R or S? Well, build the molecule, or what I'm going to start incorporating to the notes, a way you can do this from the Fischer projection, and I really don't want to teach it to you this way because I'm afraid a lot of you are going to do it wrong, but write it out like a number. So 1, 2, 3, 4. Find the lowest priority group. So in this case, 4. and swap it with whatever's on the right side. So erase the 4 and replace whatever's opposite on the other side. So we'll get something that looks like this. And now you look at the order. So it goes 1, 2, 3. This is counterclockwise. It's S. So this is going to be something that appears next semester in terms of the updated Chem 251 notes. There is a way to do this from Fischer projections. The big reason I don't teach it, and I'm trying to find a way to teach it so students won't get into this bad habit, they will manipulate the molecule to figure out the R and the S, and then they don't reset back to the starting molecule for the next chiral center. So they end up getting the next one wrong because they forget that they manipulated the figure before. So I'm probably going to try to use this methodology. Yeah, I got it right. It's S. It's always your fear as an instructor is that you've just been teaching it wrong for years and didn't know it was wrong. Or in my case, teaching it for months and not knowing it was wrong. All right, we got 3 more minutes. What questions are out there? You're welcome. So just as a reminder, tonight the homework is due. You have Saturday and Sunday to take the exam. You have, if you're taking one of my students, you have 75 minutes to take the exam. It's 20 multiple choice questions, 5 points each, but they all weigh the same. So super hard ones weigh just as much as easy ones, which is how we're getting around the fact that there's no partial credit for these problems. But I will try to be around by email, but it's not really likely that I'm going to be able to respond to an email while you're taking the exam. The big thing you need to tell me, if you take the exam and there's a problem that is completely out of left field, meaning like you've never seen it before, you're pretty sure we've never gone over it, it's not in the notes anywhere, send me an email with the problem number. So it draws from a pool for your exam, so if I were to take it, it's going to give me a question. It may not be your question, but after you've taken the exam, I can see what question it gave you. If it is definitely a question that we didn't cover or it's just something really weird or unfair, I will give the entire class credit back for that particular problem. So again, take a look at the exam. As with all my courses, the homework is meant to be harder than the exam because the homework you have time to work on, you have time to collaborate with. The exam is kind of a measure of your own skill sets, so I don't see a reason to be super hard on that regard. All right, I will see some of you Monday for the live stream, and I will see some of you live Tuesday when we go to lab. Thanks for showing up.